All right, so looking at finding zeros using graph, okay? A zero is the value of x that produces an output of zero. Okay, so it's the x value that makes y zero. Okay? So if you think about what a zero is, whatever the x value is, that gives you a y of zero. Okay? Well, this shouldn't be new to you. You guys have seen this before, right? Whenever y is zero, we're talking about the x-axis. So if we're talking about the x values of the function that touch the x-axis, then that means we're talking about the x-intercepts. So zeros are the same as x-intercepts. So if we're using a graph to find the zeros, that means all we have to do is look at the x-intercepts on the graph. Well, that's pretty easy. Okay? So zeros are the same as x-intercepts. With my Algebra 2 students, I get on pretty hard about remembering that there's four terms that really mean the same thing in this context. Zeros, x-intercepts, solutions, and then roots. And we don't use the word roots a lot, but it's in there. So zeros, x-intercepts, solutions, and roots. We were just talking the other day about solving. Okay, so how that ties in with what we're doing today. Okay. So if I want to use the graph to determine the zeros, that means I'm using the graph to look for the x-intercepts. Okay. So I'm seeing that x-intercept. So when you say zeros, that's just the x value. Okay. So all I want to know is the x value there. So that's x equals -1. That's x equals +1. And that's x equals 5. So there's our zeros. Okay. I do believe that the WebAssign asks you guys to order them a lot of times from small to large, so it will look pretty much like this. Okay. And it's pretty straightforward most of the time. They give you the graph, find those x-intercepts. So those would be the zeros on those two functions. Anything there on example 1 you guys need to go over? Okay. All right. So next thing it says, zeros can be repeated in function. Okay, so for this function, I want to sketch this real quick to help you guys see this. So if I sketch the graph, f of x equals x squared minus 6x plus 9. So, this is a quadratic, so it's a parabola. Its y-intercept is at 9. Okay. If we factor to try to figure out what its x-intercept is, it would look like this, x minus 3 and x minus 3. And so the x-intercept would be at 3, and the other one would also be at 3. So it has a double x-intercept, or the same x-intercept twice there at 3. What this graph ends up doing is bouncing at 3. And I know it's something I talked to my Algebra 2 students about last year, the idea of a bounce in a graph. Okay? What we're seeing here is what they're calling is a repeated zero. Okay? So it has the same zero twice, same x value twice, and so it's a repeated zero. I call that a double root. The phrasing here doesn't really matter, but again, any of you guys that were with me last year might remember that term as a double root. But with that double root, what we see is a bounce. Okay, so that same zero can show up multiple times. It doesn't have to be 2 times. It could be 3 times. It could be 4 times. It could be 12 times. With a double root, particularly, we see a bounce, and that's all we would have seen last year. We're going to talk today about more of those, and that term that we use to talk about that, because it is repeated, is multiplicity. So it has a multiplicity, and then specifically has a multiplicity of 2. So multiplicity is just the number of times that a particular 0 or root shows up. So that one had the same 0 twice, so it has a multiplicity of 2. You can have multiplicity of 1, you can have multiplicity of 5, you can have multiplicity of 12. There's no negative multiplicities, there's no 0 multiplicities, there's no fractional or decimal multiplicities. Okay, they're only the counting numbers. Okay, so how many times does a particular 0 show up? Okay, is what a multiplicity is. Okay? So we're going to be given some polynomials that are already factored, and it's going to ask us to identify their zeros and then what the multiplicity of those zeros is. Okay? So the problems are already factored for us. It wants us to list the zeros and then also the multiplicity of those zeros. Okay? Well, finding the zeros is pretty easy. We just look at what's inside there, right? You just say, well, what value of x would make that 0? Right? Well, x would need to be 1 there, right, in order to make that 0. What value of x would make that 0? Yep, -2, right, Grant? X would need to be -2. And what value of x would make that 0, right? So nothing big going on here, right? There's our... Okay. And so then that's something you guys have done before, not a big deal. The next side of that is, what about the multiplicity of those zeros? Where do we look for that? I'll take us back here real quick. X minus 3 and x minus 3. That's the same thing as x minus 3 squared. That square and that 2 there are connected. Okay? So it's the exponent on the factor that tells us the multiplicity of the factor. Okay, so I'm looking at the exponent next to see what the multiplicity of each factor is, or each 0 is. So this one has an exponent of 1. So I'd say with multiplicity of 1. The second one has a multiplicity, or an exponent of 3. So this one would have multiplicity of 3. And then the last one has an exponent of 2, so it has a multiplicity of 2. I do believe when they give those to you guys, or when they want them back, they want them in like order from least to greatest. So you would need to order this correctly. Like, so this one would go first, and then that one, and then that one. So they will just ask you, and it'll say on the side small to large. So, but it's no big deal. Okay, so there's F. Looking at G, again, the first thing I look at is just what would be inside the parentheses. So there, I'm just looking at the X. I'm not looking at the negative. I'm not looking at the 3. I'm just looking at the X. Here I'm looking at the X plus 5. And here I'm looking at the X minus 2. And that's the first thing. So finding the zeros first, just, okay. Well, what would make that 0? Well, if it was 0, it would be equal to 0. What would the next one 0? That'd be -5. And the last one would be +2. Then I look at the exponent. So there are 3 solutions of 0. So, okay. The next one has an exponent of 1. It has a multiplicity of 1. The last one has a multiplicity of 4. So again, kind of the idea is that means there's 3 zeros, 1 negative 5, and then 4 2's. So there'd be 8 solutions to this. Okay? But there's only 3 unique solutions. Okay, so there's 8 total, but there's so many repeats, there's only 3 unique. Okay? Any questions there about being given a factored problem and then finding the zeros, figuring out multiplicity? Okay. All right, so we're going to take that and add a layer to it. So I need you guys to write this down. So basically now the problem is not factored. We kind of want to do the same thing. Okay. So find a place to write this down. Notice they're asking us to find the p-intercepts. I don't normally know about p-intercepts, but I would notice when it says find p-intercepts where p is inside the parentheses where x normally is. So finding p-intercepts and finding x-intercepts is the same thing in this situation. Okay, so they're just asking us to find x-intercepts. We find x-intercepts by finding zeros. We find x-intercepts by solving. Right? We should know how to solve this equation. Okay? We've done lots of. Okay? So we're just finding x-intercepts. We're just finding solutions. We're just finding zeros. Okay? That's all it means. So think about how the last ones were so easy because they're already factored for us. So that's kind of our first step here is to get this into factored form. Well, using a word like factor is a pretty big word because factoring can mean lots of different things. So we kind of start running our process. How do we factor? So what should we do first if we're wanting to factor this? Yeah, right, Maddie, right, Grant. We want to do GCF first, right? Or just check, right? Is there a GCF? That's always the first question you should ask. And well, it turns out in this one there is, yeah. So let's definitely deal with that GCF first. So they all have p in them, right? P cubed plus 2p squared minus 32. Okay. Yeah, but good chance we're not done factoring yet because there's so much going on still. So what's the next kind of thing? What's the next piece of this path through this problem factoring? Where we notice they all had a p, so we dealt with that. So the next thing should be screaming at you. Okay, Riley, can you say that publicly and then also add on why you're saying that? Oh, yeah. Thanks, Maddie. Sorry, I had a right-o there. Riley, did you hear what I asked you to do?
Don't you group it because you're to simplify even more and to like get into their own
But how
little
do you know to
group?
do grouping is what I'm asking.
Because P2 can go into P3 and then like 16 can go into 32. But, like
You're not getting into the why we can do it. You're kind of getting more to how we do it. How did you know that grouping was the right way to go?
it's new. I don't
Grouping
what
only
how
works
like
on certain types of problems. So when can we do grouping, guys? It's not quadrant. That's not a word, Katie. 4 terms, yeah. Quadnomial. You're silly. Yeah. Yeah, 4 terms for grouping, right? Yeah, so then like Riley was saying that the first two do both have a p squared in them. So take that out, it leaves us with p plus 2, and then like she said, the second two both have a negative 16 in them, which also leaves us with a p plus 2. Make sure you close that first set of parentheses. And then they both have p plus 2, so that comes out. Don't lose that p. We have our p squared minus 16. Okay. Are we done factoring now? No, we're not. Okay, so Grant's saying we need to deal with that p squared minus 16. So what's that? What type of factoring is that, Grant? Remember what it looks like when you're done? There you go, difference of squares, right? And then Grant knows the difference of squares. Bring down it all the other junk. P plus 2, and then the difference of squares are nice and easy. P to P, 4 and 4. So far as what you guys are going to see in the homework, there's no AC method to any of the factoring. It's purely grouping, GCF, and difference of squares. So I just took all 3 of those and just squished them into one problem. So you guys won't have one this big, but it just kind of represents all the different types you guys will see. Okay, so that's the factoring, right? That's step 1, get it factored. Okay. Well, thankfully step 2 is easy. All right, find those p-intercepts. So, what does p need to be in order to make y 0? Well, 0, negative 2, negative 4, positive 4. And again, I think they ask you guys to write them in order, least to greatest. The other thing here is that they want intercepts, which are points. Okay, they're not just values. Zeros are the x value that makes y 0. Y-intercepts are points. They have x and y coordinates. Okay, so you need to make sure you're writing them as points. So the smallest one there being negative 4, and then negative 2, and then 0, and then 4. All right. So those are the x values when y is 0, or the x values that make y 0. Sorry. Anything there? You guys want to talk about? All right, let's head back to the normal stuff here. So we talked about multiplicity. Next thing I want to do is talk about what multiplicity looks like. Where we want to head is, can you look at a graph and talk about the zeros and the multiplicity of those zeros? So it'll be like what's happening here on the next page. Or can you be given some information about the multiplicity and the zeros and stuff and sketch a graph where really what you guys are going to have to do is pick a graph out of a group of 4. So, okay. So what's the visual side of multiplicity? Okay. So there are 3 ways that it shows up. So when we talk about these real zeros and the way that they touch or interact with the x-axis, or whether the graph will interact with the x-axis at those points depends on the multiplicity. There's just 3 basic ways that it'll happen. Okay. So I've just sketched out some quick sets of axes. Okay. So a single factor. This is the one you guys are the most used to seeing. Okay. If we thought about like a graph or a function like x squared minus 4. Okay. It's a parabola, its y-intercept is at -4. If we were to solve that, find its x-intercepts, the x-intercepts would be 2 and -2. Okay. It would look something like this. Okay. It's a parabola. So it would look something like that. There's a multiplicity of 1 here and there's a multiplicity of 1 here. I'm going to draw another graph before I talk about what it looks like. Another pretty simple graph that to see would be something like just a line, like 5x minus 7. Okay, a very steep line, right? Whatever that number is there, it also has a multiplicity of 1 at that 0, okay? So what do we see? What does it look like when there's a multiplicity of 1? So all we're doing right now is describing how the graph acts around that point. Okay, that's all this type stuff is. Okay. So when you look at that x-intercept, the graph is just passing through that point. There's nothing really special happening there, right? It's just passing through or crossing the x-axis at that point. Okay. I usually use the phrase pass through. Okay. You might hear somebody else say something completely different. Again, all I'm trying to do is be descriptive of what I'm seeing happen right in this area. Okay. The graph is just passing through that point. The graph is just passing through that point. That's all that's happening. Okay. So with a multiplicity of 1, we see just the graph just pass through the point. Nothing really special happens then. Okay. We're pretty used to seeing that happen. Something we're a little bit less used to seeing happen, but we've seen happen. We just saw it happen up here. Okay, when there's an even multiplicity, we get that double root or a quadruple root or a sextuple root or whatever you want to call that. Okay. So if we think about that problem that we just did over there, which was x squared minus 6x plus 9, we saw it hit the x-axis and then bounce. Okay. So that's 3. It has 2 3s at that point. And there's 2 answers. They're both 3. It bounces at that point. Okay. Another example of something that would do this, like another even factor, right, would be something like if I did x to the 4th, but just like negative x to the 4th. X to the 4th is essentially going to look like a parabola. It's going to look like a skinnier, kind of flatter bottomed parabola, but essentially looks like a parabola. And then if I make it negative x to the 4th, it's just going to flip it upside down. But it's going to touch right there at 0, 0. Okay. So that could be something about what negative x to the fourth would look like. So there would be 4 answers to that. They would all be 0. Okay, so that 0 has 4 roots there, but still is just a bounce. Okay? Sometimes you might hear it called a turnaround. Again, I like to use the word bounce. Okay? So even factors, even numbers of roots bounce or turn around at that point. Okay? Again, this one would have 2 factors of 3. This one would have 4 factors of 0. But either way, it just bounces at that point. Okay? You've seen that happen, bounce off the x-axis. That's not brand new to you guys. Okay? And the last set is if it's odd, but anything more than 1. Okay? Again, there's no 0, there's no negatives, there's no fractions or decimals. It's only counting numbers. All right? So what if there's 3 roots, 5 roots, 7 roots, 9 roots, all the same thing? Again, you guys have seen this before. Right? This is not a brand new function here. Simplest one I could think of would just be x cubed. Right? X cubed would 0 cubed is 0, 1 cubed is 1, 2 cubed is 8. Right? Negative 1 cubed is negative 1, negative 2 cubed is negative 8. You guys have all seen the x cubed graph before. Looks like that stretched out vertical S. So it's 3 solutions, it's 3 roots, it's 3 x-intercepts would all be 0. So it shows up 3 times. What's happening at 0? So I think of the graph kind of being like twisted right there. So it is passing through 0, just like it does with 1. It passes through, but along with the pass through, it gets twisted. Okay? Or it kind of flattens, or like it flattens for a second and then it goes back up sharp. Okay? So again, I call it a twist. Again, you might also hear it called like a flattening. Again, what we're describing is what happens near the x-intercept. So the graph gets twisted or the graph gets flattened near the x-intercept, and then it shoots off again, right? It's not flat here by any means. It's getting flatter, kind of squished there a little bit. One that would be a little bit more extreme would be something like x minus 5 to the 7th power or something like that. So out here at 5, the graph would probably look something like this. Like it would get really flat there in the middle. Like it's still going to have like the slightest little bit of angle to it, but it looks really flat to us. And then it shoots off really sharp again. Okay. But you can see definitely kind of the graph looks a little twisted. Okay. So that's the word I like to use. Yeah, what we're going to be doing with this, you guys are going to be given a graph, given a function. We're going to sketch it us. But you guys are just going to use that to pick out from a group of graphs which one's the right one. We're also going to look at a graph and say, well, what's happening? How many 2s are there? How many 3s are there? Stuff like that. So as far as what we're going to do, anytime you guys see a bounce, it's going to be a 2. Okay, it's really hard to tell the difference between a 2 and a 4 and a 6 and an 8. Okay, we will only use anytime you see a graph there bounce, it's going to represent a double root. Okay, we won't get any higher than that. So any even thing will be a 2, and in the same way, any odd number bigger than 3 will be, or sorry, bigger than 1 will be 3. Okay, so if you see any twists, you can assume that it's a 3 multiplicity, not a 7 multiplicity. Okay. So the only 3 choices we will have will be 1, 2, and 3. Okay. It's very difficult to tell the difference between 2 and a 4, between a 3 and a 5. You need more information than we're going to get into. So, okay. So when I look at this, I know that's a multiplicity of 2 there, not a multiplicity of 4 or a multiplicity of 6 or something like that. Same way, I know that this is a multiplicity of 3, not a multiplicity of 5 or 7 or 9 or something like that. Okay. So. Anything about the way the multiplicities look you guys want to talk about? All right. There's just one other thing we need to talk about before we're ready to move on to this next problem. It's kind of a bigger thing, but something you guys have done before, so I'm hoping just to be able to access that information. And it's really not too big of a deal for the problem. I think you guys will have enough other information to be able to pick the graphs out of the group without having this, or be able to like kind of know it. So I'm not super worried about this, but it's definitely something you guys learned last year, which was end behavior. So I want to kind of touch on it just to make sure you guys, I'm not leaving you hanging on it, but this is definitely like a big idea that we would have learned last year that can be kind of confusing. And so hoping that that information is back there still. And when you guys hear me talk about it, you're like, oh yeah, I remember that. We'll be able to use it enough for what we're doing, because it's not a big part of what we're up to today. So end behavior, I just sketched out 4 little axes real quick. We need to think about what the degree of the polynomial is. So if there's even degrees, or if it's odd degrees, if it's like an x cubed, x to the 5th. When we talk about degree, it's the highest exponent in the polynomial. So just as an example, something with even degree that you guys would be really familiar with would be like x squared minus 3x plus 5. That would be a graph that we could have graphed already. Okay. What we're talking about here is, what do the ends of that function do? When we look at the graph, what do its ends do? Purely about the ends. Okay. Has nothing to do with what's going on in the middle. Well, what would this graph look like? It's a parabola. It opens up, right? What are its ends doing? Well, they're pointing up. Okay. The same way that 2x to the 4th minus 3x cubed minus 7x squared plus 5x minus 2. The ends of this function would also point up, as they have an even degree. Oh, sorry, and I forgot to mention this last part too. And also a leading coefficient that is positive. So this number is positive, and this is even. The ends will point up. The middle will do all sorts of wiggly wobbly things if you want it to. That just depends on all the other stuff. Okay? But the ends will point up. Okay? There's so many different ways for you guys to access this. Okay? The simplest even degree function out there is x squared. What do the ends of x squared do? You guys should all know that. Yeah, they all point up. It's easy. Okay? The way I described it with my Algebra 2 students was, just think about a letter that looks like that. Notice that kind of looks like a W. So if it's positive even, it looks like a W or a U. Okay? The ends point up. Positive even was a U or a W. The ends point up. Okay? It's x squared. You know what x squared does? It's a W. What do the ends of W do? Okay? What if it's still even, but now that our leading coefficient is negative? Well, what do I do to my W? It's negative now. Flip it upside down. Okay? So what goes on in the middle? I don't care. Okay? But what I'm caring about here is, what do the ends do? So even degree, negative leading coefficient, upside down W. Negative x squared. Right? You graph negative x squared, you should know how to do that. Right? You should have a picture of that in your head. Okay? The other thing to think about is, think about the word even. You need a different way to access it. What's the word even mean? If things are even between us, things are the same between us, things are fair, right? Look at the ends. They do the same thing. They both go up or they both go down. If you know that they both go up or they both go down, then the positive or negative should be enough. Okay, it's even, both, even, both, even, both. Well, they're both up or they're both down. You should be able to figure out the up or down part very easily. Okay, if it's negative 2x to the fourth plus blah, blah, blah. Okay, the rest of it doesn't matter. All I care about is that this is negative and that's a 4. Okay, negative and even. The rest does not matter. These will point down. Okay. Well, if even is the same, odd would have to be different, right? Well, if I'm odd and positive, positive is kind of the normal way for things to act, right? Well, as we move to the right, well, that's positive. Up is also positive. So the right end would move up. As I move to the left, that's the negative direction. Well, down is also the negative direction. That's normal, right? So the left end would move down. And what's the middle doing? Don't know, don't care. Okay? But if it's an odd degree, like x cubed, right, we drew x cubed a little while ago. What did the ends do? Right end went up, left end went down. And there's a one way to think about it, right? What's x cubed look like? Okay, what do the ends of x cubed look like? Another way to access it, what letter does that look like? Okay, I talked with my students last year about W and N, right? That looks like an N. What do the ends of N look like? Right? The right end goes up, the left end goes down. I want to talk about an N. Okay? And then the other way was, right, if even means the same, odd means different, they go in different directions. Again, you should be able to figure out the positive, negative side of it. Last thing here, what if it's odd but negative? Well, if odd positive is an N, odd negative would be an upside down N. What do upside down ends look like? Okay? That means the right end is going down, the left end is going up. What happens in the middle? Don't know, don't care. Okay? And all we're going to do with this is going to be using it as, you guys are going to use it as one part of your process of elimination stuff. Okay? We're going to do this next problem where we're going to have to draw it, so we have to do some more thinking than that. But you guys can just look at the problem and say, hey, I've got a negative even problem. Both of my ends better point down. I can eliminate any graph where both ends don't point down. That could kill off 2 graphs right there. Maybe it only kills off 1. Maybe it doesn't kill off any, right? It's just one of the tools you guys have to use for process elimination on your problem. Okay? Maybe you need more time here. Sorry before I scoot on. There's a lot of stuff there just for a little bit of help, hopefully. Okay, so again, what you guys are going to end up doing will be picking the graph out of a bunch. It's going to say, note the x-intercepts, y-intercepts, multiplicity, and behavior. So I'm going to talk to you about how to use those pieces of information to basically process of elimination stuff. Okay. First thing we want to do is look at the x-intercepts for this function. We've already talked about that. All right, that's just x equals 0, x equals 3, and x equals -2. Okay, so those are our x-intercepts. So you go to your graphs, right? You got 4 graphs, and you can get rid of any ones that don't have these 3 x-intercepts. Again, we're gonna sketch this, but Okay, so you notice that there's one that doesn't cross at those 3 points. Boom, it's gone. And now you're down to 3 graphs. Okay. Next thing they want us to talk about is the y-intercept. What's it mean to be a y-intercept? Well, if it's an x-intercept, that means y is 0. So for a y-intercept, x must be 0. You guys know that? So I plug in 0. Well, 0 squared is 0, negative 0 is 0. 0 minus 3 is negative 3. 0 plus 2 is 2. 2 cubed is 8. Well, 0 times anything is 0. So our y-intercept is 0, 0, which shouldn't have been surprising because that. So any graph that doesn't cross the y-axis at 0 also could be eliminated. But there, that point's doing double duty. That's the x-intercept and the y-intercept. Then they want us to talk about the multiplicity of those points, those intercepts. Now that's all about the exponent. 2, that's even. 2 is even as a twist, or sorry, not a twist, a bounce. So this graph better bounce at 0. That's a 1. 1 was just a pass through. The graph better just pass through 3. 3 is a higher order odd, so that means that was our twist. So at negative 2, our graph better twist. Again, do I have a graph that bounces at 0? If I have one that doesn't, boom, it's gone. Okay? That's what you guys get to do. Eliminate stuff that doesn't match what it should. Okay? The last thing here is the end behavior. You know, it's a lot of stuff. End behavior. Okay. What I need is the degree. This is a 2, a 1, and a 3. When I add those up, I get 6. 6 is even. It's also negative. So what did a negative even look like? Well, even was the same. So they both went up, or they both went down. So a negative even, both my ends should point down. So if I have any graphs that don't point down both ends, then they're gone. Okay? So all those things can be used for process elimination on your end. Okay? We're going to use all that information to graph this, or get a real rough sketch of it. Okay? You guys don't have to do this on your own, so don't worry about it too much, but I need to find a way basically to combine these ideas here, what the ends look like and then what's happening here. Right, I've already plotted these points. Okay? How do I deal with what the ends are doing and then what's the behavior at the x-intercepts? Okay? I'm going to start here on the left end. So the left end of my graph is pointing down. I know that. Yeah, I'm going to green actually. The next thing I'm going to touch is negative 2. But at negative 2, I'm supposed to twist. So as I go towards negative 2, I'm going to get really close to it, and then I'm going to flatten or twist, right? Or the twist also is a flattening. So as I get close to it, I'm going to flatten, and then go through and then go back up again. Okay, so there's my twist at negative 2. What was the next thing, right? The next thing is 0. What's happening at 0? There's a bounce. So I need to bounce on 0. So I have to go up before I can come back down, right? I don't know how far I'm going up. I don't know. But then at some point I have to turn around, going back towards 0. At 0, I'm bouncing. Okay? So the amount you choose to do this is really up to you. There's no way for us to know that. The amount that you go up. It's not going to go like straight over. Okay? It'll go up some, then come back around. Okay? Usually my kind of idea here is the further apart these are, the higher it goes up. So like these two are further apart, so it's going to go up higher. And these two are so close together, it can't go up very high. So next thing I'm going to hit is 3. what happens at 3? It's going to pass through 3 and then keep going down. So it's going to go up a ways. Again, we don't really know how much, but it should go up higher than the other one because it has further to go. And it's a head towards 3, and then just keep heading down forever. Because there's our end behavior, down, both sides down. So if we threw that into Desmos, the graph would look kind of like that. Okay. So it's taking all those ideas and combining them into getting, again, you guys get to do it the easier way because you just get to pick the graph out. A lot of synthesis there in that problem. And last problem, I know we're about done by the time. The last problem is really easy. Okay. So they've given us the graph. They want us to use it to identify the zeros in their multiplicity. Okay. Identifying zeros, that's the very first thing we did there. That's the easiest thing we can do. So what are the values, right? -1, +1, and 2. And then we go to look at how is it behaving there. All right. When I look at that, I see a twist. I see it getting flatter there. Twists come from higher order odds. I told you guys it would max out at 3. Okay. Here at 1, it's just passing through. It's not doing anything weird. Okay, it's just a pass through. Pass throughs come from 1s. Multiplicity of 1. And there's a bounce. Bounces come from evens. I told you guys it would max out at 2. Okay. That's all that is. Yeah, it's just a coincidence that these numbers here are the same. So they have nothing to do with each other. All right, I know that was a lot of stuff.